Okay, so I have Kerstin Bear. We'll talk about quantum neural nets.
Yeah. Hello, everybody. First of all, I want to say that I'm really impressed by all the talks I heard this week. It was really nice. Thank you so much for the organizers to put this nice program together. And thank you for giving me the opportunity to speak about quantum neural networks. My plan is to first introduce neural networks more generally, to give everybody the chance to be on the same page, and then we will talk about quantum neural networks. And to make it more hands-on, I will discuss dissipative quantum neural networks, so one example of quantum neural networks in more detail. And yeah, we actually came up with the idea of dissipative quantum neural networks during my PhD back in Hanover at the Leibniz University. I did my PhD in the group of Tobias Osborn and Reinhard Werner. And I'm still working on quantum machine learning, but now I'm doing that from down under. I'm a research fellow at Macquarie University. And yeah, no matter whether you're in Australia or Germany or many other places around the world, in the last decade, we got used to many very convenient tools. So our search engines rearrange and optimize results based on our user characteristics. We are used to always up-to-date travel estimates, and our email programs categorize spam or phishing emails. Similar tools can predict side effects of drug combinations or analyze computer tomography pictures and even optimize our power supplies. And yeah, what do all these methods have in common? You probably guessed it, these are based on machine learning. But yeah, what is machine learning? I want to give a quick intuition for that. So many problems we can describe and solve by deterministic algorithms. So we can find little steps and decisions, and then based on that, the computer can solve the problem for us. But there are a lot of problems, for example, when it comes to categorizing pictures, where it's even for us humans hard to describe why we know that the picture is a dog or a cat. So it's really hard for us to come up with this kind of deterministic algorithms. And therefore, yeah, algorithms where the machine learns from the data itself, then following a deterministic algorithm, come in very handy. And these are called machine learning algorithms. But how can we make a computer learn? And one answer to that are neural networks. Neural networks are inspired by the human neural network, and our brain alone consists of billions of neurons. And these neurons are connected via synapses, and every time when we learn something new, these synapses change a little bit, and yeah, our neural network changes. And the same idea got translated onto classical computers. So here the neurons are just nonlinear functions, and in the most easiest case, the synapses, the artificial synapses, are just weights. So we have some kind of weighted graph, and we transport the information through the network. Usually, these neural networks are structured in a lot of layers. So we call the first layer input layer, and then we have a lot of hidden layers and some kind of output layer. Let's do a quick example before we go to the quantum case. The most common example is learning handwritten digits. You will find it all over the literature. And here we have a very standard supervised problem. So we have data pairs of an input and a desired output. In this case, the input would be a handwritten digit, and the output would be the desired digit. And what we simply do, so we have many of these pairs, and what we simply do is then we input the picture into the neural network, so we translate it into a vector, and then we follow all these functions, and at the end we get some output. I will not go in detail about the classical functions because it's not important for us now, but we get some output. And what we then do is we compare the output with the desired output. So there are many functions, and we get some kind of results, and based on this example, we will compare the 7 to the 1 and then see how good is our neural network at this stage. And at the beginning, all these weights are initialized in some kind of way. And then after we saw a lot of these training data pairs, we update these artificial synapses. And after seeing tons of data pairs, the neural network would be able to categorize handwritings of people which weren't included in the data set. So we call that generalizing. Okay, so that's the basic idea of supervised learning of neural networks. But yeah, we are here to talk about quantum devices. And yeah, what is quantum machine learning? That's actually a good question because it's not so easy or not a direct answer. Because in classical machine learning, we have a classical problem and a classical algorithm. But there are three different ways how we can include quantum into that. So the first idea would be still having some kind of classical problem, but then like decoding the classical data into quantum data and using some kind of quantum algorithm to learn it. So we have some kind of quantum machine learning algorithm on classical data. That can be basically used for every classical problem. But then there's also another category where the data is quantum, but the algorithm is classical. This is also sometimes included into quantum machine learning. So here we, for example, study many-body quantum systems, and we have some kind of problem which we formulate in our quantum way, and then decode it into classical data and use some of these millions very, very good classical machine learning algorithms to solve it. And there's the last category. So here we have quantum data and a quantum algorithm. So our motivation to work in this last category was that we have more and more quantum devices and get more and more quantum data, but we don't have many applications or many methods how to deal with the data directly. And therefore, we were interested in algorithms which can learn directly from the quantum data. So we don't have to translate it into some other classical data. And one example for that would be having some kind of supervised problem. So here we can imagine we have a black box and we put one input state in, and we know which kind of input we put into the black box, and then we get some kind of state out, and we collect these pairs. Here we decided that the output is a pure state. It makes things easier, but this whole thing is also generalizable for mixed states. But so we collect a lot of these pairs of two quantum states. And what we then want to aim is to learn a relationship between these two states to just find out what the black box does. And for that, we can use quantum neural networks. And there are very different approaches for quantum neural networks, and I would categorize them in two groups. The first one is where we have layers of operations. And on Wednesday, we talked about the QAOA algorithm. And basically, that could be seen as a quantum neural network because we have some layers of unitary operations. And they get applied on the same two qubits in this case. So we have layers of operations working on the same qubits. So this is one category. The other category would be we have layers of qubits. So here, different to the slide before, every layer has a different set of qubits. And we came up with this idea, or we present this idea in this paper here, Training Deep Quantum Neural Networks, in case you want to read further. And as in the classical neural networks, we have an input layer of two qubits in this case, and then we have some hidden layers and an output layer. And again, we have to connect these layers, and we do that also with unitary operations. And they are structured in the following way. We have here unitaries which act on all the qubits of one layer and one qubit on the second layer. So basically this red unitary here is a 3-qubit unitary. It acts on 2 qubits of the input layer and 1 qubit of the layer number 1. And you see this little under-over crossings. These represent that the unitary is not commute in general, and the order is actually important. And so we do that with this kind of qubit, and we also connect this kind of qubit, and we can write this whole like layer-to-layer connection unitary as U1. Okay, so now we have this data set, and I want to tell you how we actually like do that, or how we feed forward our information through the network. So therefore, let's do a minimal example. So here we have just 3 layers. At the beginning, all these qubits are initialized in the 0 state, and the unitaries are just randomly assigned. And then we initialize the first 2 qubits in the input state. And then we tensor the next layer to that. So we have now a 5-qubit state. And then we apply the first unitary operation, which acts on the 3 qubits. So there should be identities here. But yeah, we will use this notation here. And then we apply the next unitary and the third one. And then we end up with this 5-qubit state here. Okay, what we then do is very important. We trace out the first layer, and we have this 3-qubit state here. And because of this step in the algorithm, the networks are called dissipative quantum neural networks, because we get rid of like 1 layer at the time and only work like with two layers in every step. And this is important because now the qubits we need only scale with the width of the network, not with the length. And we can actually work with very deep quantum neural networks. Okay, so the next step would be initializing the next layer. So this is already our last layer in this example. And then we apply this unitary operation, which is a 4-qubit unitary. It acts on all the qubits of this layer and 1 qubit of that, and then another unitary, and we trace out the hidden layer and end up with the output state. So that's an example how we feed forward the information through the network. And yeah, now we have this network and we have some kind of output. And before we get to how we actually like learn how we change the network, I want to point out something very interesting or very helpful about the network. And this is that the layer-to-layer map is actually just a completely positive map. So we can write every layer state as a completely positive map acting on the state before. And then we can do that for every layer. And at the end, we just have this long concatenation of completely positive maps. And I call the neural network with this fancy curly E from now on. So our output is E of the input state. Okay, good. So now we have the output here, and we have the desired output. And in the same way as we compared the 7 to the 1 in our earlier on classical example, we now want to compare these 2 states. And to do that, we chose to use the fidelity. So this is just an average over all the data pairs. So X is the index for the data pairs. We have S data pairs. And this is just the fidelity of the output of the network with the desired output. And in the optimal case, this whole loss function, supervised loss function, would be 1. So then in this case, every output of the network would be actually the output we wanted to have. There are, of course, many choices we can make for the loss function. This is just one. The argument for that is it works. So that's like often the case in machine learning. If it works well, if we can see a training progress, then it's good. Okay, good. Now we have these unitaries. And as I told you before, these were initialized randomly. So we have random unitaries, and then we see the training data pairs, and we want to update them. Yeah.
So when you look at the fidelity, the output state is a mixed state, right? But so to get 1, you need a pure state. Does that mean that it's just a product state of all the layers?
Sorry again?
So when you do this tracing out, you get a mixed state, right? If they're entangled, if the layers are entangled. But to get fidelity 1, you need a pure state, right?
Yeah.
So does that mean that in the end you need a product state over the layers to get fidelity 1?
Yeah, I think so. Yeah, but we also generalize this for the case of a mixed state, and then it's differently. Yeah. Okay, but now we have to update the unitaries, and for that we chose that our update rule should look like that. So we have the matrix U at time t times some kind of update matrix, and this important bit is this update matrix K here, and then we get the next step unitary. And what we basically did is we maximized our loss function, so the fidelity loss function, to derive how this matrix K should look like for every training step. And I won't show you the whole formula. I'm hiding here something in this M because it's very ugly, but I will give you an example. So for this little case here, when we update this unitary 1, 2 with the update matrix K, we can see how this update matrix is actually done. So here we have some kind of learning parameter. This here comes from the size of the layer. And then we have this big commutator here. So this is one part of the commutator and the other part of the commutator. And it's very intuitive, actually. So in the first part of the commutator, we have the input state going forward to the network. So the input turns out with the next layer and then applying the 2 unitary operations until we get to this unitary we want to update. And in the other side of the commutator, we have the desired output state going backwards through the network. So here we have the identity, and then take a look at the daggers. We're going in the other direction, tracing out, and until we end up with this unitary, which is 1 before the unitary we want to update. So basically, the commutator in this update matrix is just comparing the feed forward of the input state and the back-propagation of the desired output state. And I want to stress out that we did not think about the structure. We just derived it by optimizing the fidelity. So we were very happy when we saw that because we gained some intuition how the neural network actually worked. Okay. And we trace everything out. And then, we have this matrix K, which is used in this update rule. Okay, so now we have this loss function, so we know what our aim is, what we want to learn. We have our training data pairs. We know how to compare these 2 states. Now it's time to look a bit closer at the training data. So we did it in the same way as classical machine learning people do it. We just split our training data into some training data and into validation data. So here's the training loss you already saw, and then the validation loss is basically the same in this case because it's a very easy example. So it's also the fidelity, but it's going over the n-s validation training data pairs. And when we look at our training, we only look at the validation loss, so only the data pairs we have not seen during the training process. Okay, now we come to a real example because I told you at the beginning that I'm thinking of some kind of black box, and here we assume that the black box is just an unknown unitary y. So the input times an unknown unitary y is the desired output, and our aim is now to learn this unitary here. So we produce a lot of these training data pairs and then train our algorithm, our neural network with that. Okay, here you see a class. Yeah, I'm coming to that now. So here we have an example for that. This is a classical simulation of the whole process, to keep that in mind. Yeah, the number of qubits, we have 2 qubits. So we're comparing 2 qubit states because the input layer is a 2 qubit state and the output layer is a 2 qubit state. And we decided to have 20 data pairs, and 10 of them were supervised and 10 were used for validation. So a very small example. But already for that, very small, like 3-layer, only 10 validation, 10 training pairs, we can see that the training works because the unsupervised loss function, so the validation loss, reaches 1 after like 1,000 of training epochs. So in every of these epochs here, we see all the training data and update all the unitaries. And then at the end, our neural network is perfectly trained, and we can simulate this unknown unitary Y, so the black box.
Do you have do you use as data the full kind of set of superpositions, or do you have a discrete set of data there?
So we use just the data pairs. So we assume we have like 10 pairs of quantum states, and we have the input and the output.
But you can have whatever 0.1 plus 0.9 something I 0 for the first, and you can have entanglement and whatever. So in principle you can have all possible kind of 2 qubit states.
Yeah.
Or do you limit yourself to?
Yeah, we just limit ourselves to the data set we have.
I think
That's not what I mean.
Just an arbitrary 4x4
Yeah.
Oh, we don't limit ourselves to any like kind of specific states. We just have random states. Yeah. Sorry for not understanding your question. No, I know what you mean. Yeah. Yeah, we have just some random states we produce like with this unitary we want to learn. And then our first question was, what happens if we vary the number of states, the number of training states, so S, and we varied the number, and then we could see in this example, out of 100 training data pairs, when only 6 got used for training, we have a fidelity of 0.9, which is already pretty good. And we did similar experiments like that. But yeah, I want to end my talk with a little bit of overview what was done like after we thought about the structure and like this architecture and what like else happened with that. So the first thing was that we tried to run this whole thing on quantum devices. So we used the IBM Quantum Cloud, and there we did very small examples of neural networks, and we could still see that we have some kind of training behavior, so the loss function would increase, but of course we would not end up like with a fidelity of 1 because of all the noise. In this project, we also compared the task of learning an unknown unitary with the QAO algorithm for the same task, and we just compared how it works. And we saw that the DQNN, so the dissipative quantum neural network I just presented, is a bit better in this task, but the QAO algorithm does the job as well. But yeah, it was interesting to run this on actual devices. Then we thought more theoretically, like, can we find or can we derive a bound for the task of learning an unknown unitary? So about how many data pairs do we need to learn something? And we derived the so-called quantum no-free lunch theorem, which is the quantum analog in this case of the no-free lunch theorem, which is used in like classical computer science. And we saw that the DQNN was pretty close already for on how well it could learn for a certain number of training states. Then we tried different architectures. For example, here we had a generative adversarial network where 2 networks like fight against each other, and we have just a different loss function. Another network architecture which got tried was some kind of autoencoder where colleagues of mine tried to denoise some quantum states. Another work was where the networks were connected in some way that we have a recurrent neural network. And so we can actually learn time evolutions instead of just having fixed data pairs. And also, I was working a lot on including graph structured data. So in the case where we know a bit more about the data pairs, so about the connection of the different data pairs and how to include different loss functions in the training process and how this changes our results and our, the behavior. So these were the projects we already somehow did. But of course, there's a lot of things to try. And I will just name a few things which I'm interested in to close up the talk. So of course, we are still interested in new architectures and changing the layers. I mean, there's so many classical neural networks out there, and there's so much motivation and so many ideas what we can try. In the moment, I'm thinking of adding some measurements in this process, and trying to add a few things to the whole thing. Also, this neural network got only tried out for quantum tasks, not for classical tasks, but of course we can encode some kind of classical problem into quantum data and then also try to learn it on the dissipative quantum neural network. That's also some direction I would be interested in. Also, I'm very interested into quantum kernels, as nearly everybody in the quantum machine learning field right now. So I try to understand what the connection, or how can we express the dissipative quantum neural networks with quantum kernels and how the connection is. So that's one big interest of me in the moment. And also to deal more with noise, because we tried out training the neural networks with noisy data, which was interesting. But I would like to understand how noise gets transferred through these kind of quantum neural networks and what happens with the noise during the training process. And if you have other ideas, I'm very happy to chat with you about that. And with this little overview, I would like to thank you for your attention.
Thanks for the talk. I'm interested in learning about how flexible the unitaries that you have in the middle are, because it seems to me, if I understand correctly, you're trying to learn a 2-qubit case. So it could be that the first connections between the top 2 layers are exactly reproducing your unitary Y, and then everything else is just the identity. And so have you tried looking into having very restrained unitaries in the middle and then reproducing a unitary that no individual edge can do?
No, we didn't look at that. But I was actually thinking about that, because now also in the classical machine learning world, a lot of people think about interpretability and expressibility and stuff like that, and trying to find out what the network actually does from layer to layer. And that would be some question in this direction. I haven't worked on that, but it's interesting.
Sorry, I must have missed something, and I apologize, but how do you put the dissipative step, so you're tracing over step until function?
Okay, that's a good question. So basically, it just looks like that. So we have, in the most easiest case, you would have all the qubits in the first layer, and then we would just initialize the first qubits, the input qubits, the desired output on some kind of qubits, and the input on some kind of other qubits. And then we have these extra qubits, which we use for this layer to layer. And now there comes an important point, because at the beginning when we did that, it was not possible on the IBM cloud to reinitialize qubits. So we could actually not use the dissipative dissipative character of our neural network. But now it's possible. So now you can reinitialize qubits again, and then we can use this bunch of qubits for all the layers. Yeah.
I was just curious when you mentioned noise, what your thoughts are about, or if you've explored zero noise extrapolation or those kind of methods on top of the method that you're working on, and what are your thoughts there?
Yeah, I didn't do that, but that would be also interesting. Yeah, as I mentioned, I'm interested in noise in general, like understanding how it works and what we can do. So yeah, that's definitely a direction I'm looking into that in the moment. But I have no insights, sorry.
Okay, if there are no further questions, thank the speaker again. We're coming back at 1:30, and there's one more talk. It's a very exciting talk about simulating the latest USTC Gaussian